All right, welcome. Today, we're cracking open the secrets hidden deep inside solid metal. We're talking about the atomic code, the very instructions that dictate how strong and how tough a material is going to be.
Okay, let's dive right in. The first thing you have to understand is that not all metals are created equal, and the real difference? It's often microscopic. We're talking about this invisible architecture, this hidden world that exists inside every single piece of metal.
So right here, this shows you the core problem that metallurgists are always trying to solve. See, when metal freezes, its internal crystals, we call them grains, they tend to grow really big. This creates these long, easy pathways for cracks to just zip right through, which makes the metal weak. The goal is to get the complete opposite, a structure made of tons of tiny, tightly packed grains. It's kind of like a maze. The more twists and turns, the more boundaries there are, the harder it is for that crack to find its way through. That's what makes a metal both strong and tough.
So how do we actually do that? Well, here's our game plan. First, we're going to look at the basic physics of how these crystals are even born. Then, we'll get into the really cool stuff. Two key techniques, seeding and something called solute control, that let us engineer this internal architecture to build the incredible high-performance materials that our modern world relies on.
All right, let's zoom all the way down to the atomic level and start at the very beginning, the birth of a crystal. You know, solidification really just happens in two steps. First, you've got nucleation. That's the spark, the birth of a brand new crystal. And then you have its growth.
So here's the thing. For a crystal to even think about forming, the liquid metal has to be cooled below its normal freezing point. It enters this super chilled liquid state we call undercooling. And that state is what creates the energy push, the driving force needed to kick the whole solidification process into gear.
And this right here? This visualizes the huge hurdle they have to clear. Getting a few atoms to clump together is the easy part, but for them to form a stable crystal that's actually going to grow, they have to overcome this giant energy hill to reach what's called a critical nucleus. Seriously, just think about pushing a massive boulder up a hill. It takes a ton of effort to get it to the top, but once it's there, it can roll down the other side and grow all on its own.
Yeah, because that hill is so steep, having crystals just form out of thin air, we call that homogeneous nucleation, is incredibly rare. I mean, for pure iron, you'd need to undercool it by, get this, a whopping 420 degrees Celsius. It's just wild. In the real world, it's so much easier for crystals to just start growing on a surface that's already there. That process is called heterogeneous nucleation, and it takes way less energy.
Okay, so that little piece of information, the fact that crystals would rather grow on existing surfaces, that's the key. It leads us straight to the #1 technique metallurgists use to get control over a metal's final properties.
So that's the big question, right? If these big, lazy grains are the enemy, how do we fight back? How do we stop them from forming and instead force that fine, strong, maze-like structure that we actually want? Well, the answer is this really clever process called grain refinement. And honestly, the best way to think about it is like you're planting a forest. Instead of just letting nature do its thing and maybe grow a few giant trees, we're going to step in and take control.
Okay, so check this out. Here's the playbook. First, we dump tiny particles, our seeds, into the molten metal. These little guys act as the perfect starting points for heterogeneous nucleation. They just completely knock down that energy barrier we saw earlier. This sets off a chain reaction, causing millions of crystals to pop into existence all at once. And because there are so many of them, they immediately start bumping into each other, which stops them from growing too big. What you're left with is a dense forest of small, strong grains.
And this is not just some textbook theory. This happens every single day in the real world. Take the aluminum alloys used in car engines. A tiny bit of the element titanium is added. Why? Because it forms these little particles of titanium aluminide, which are the absolute perfect seeds for aluminum crystals. Their atomic structure is an almost perfect match, making them an ideal template. It's like giving the aluminum millions of perfect blueprints to build on.
But wait, there's more. Seeding is a fantastic tool, but it's not the only trick in the book. There's another, much more subtle thing going on. A mechanism that's driven by the alloy's own chemistry and the specific elements we put inside it. Is this wild phenomenon called constitutional undercooling. And it's a super fascinating effect that happens right at that moving boundary, right where the solid crystal meets the liquid metal. The best way to picture this is a traffic jam on an atomic highway. As that solid crystal front moves forward, it's actually really picky. It only lets certain atoms join its structure. Other alloying elements, we call them solutes, that don't quite fit get pushed away. And the specific type of element here is absolutely critical. Some elements get rejected way more than others, and they cause a massive pileup of atoms in the liquid right in front. So what's the big deal with this pileup? Well, here's where the magic happens. A higher concentration of these rejected solute elements actually lowers the local freezing point of the liquid. So as you can see, right at the interface where all those atoms are bunched up, the freezing point is suddenly much lower than in the rest of the liquid. This creates this weird, unstable zone of chemically induced, undercooled liquid.
And this unstable zone? It becomes the perfect breeding ground for brand new crystals to just pop into existence, totally on their own, without even needing a seed. It creates this amazing cascade effect that just shatters the main advancing front and makes the final grain structure even finer.
So you see what's happening? When you combine these two powerhouse techniques, seeding the liquid with the perfect particles and then fine-tuning the chemistry to create that atomic traffic jam, we go from just casting metal to actually designing it, atom by atom.
And this table is basically the cheat sheet, the atomic cookbook that engineers use. For those strong engine blocks, they add specific amounts of titanium and boron to get those fine grains. For jet turbine blades that have to survive insane temperatures, they add zirconium and hafnium to make the boundaries between the grains incredibly strong. Every single element is a deliberate choice. This is atomic-level engineering, pure and simple.
And you know what's crazy? This level of control is actually pretty new. For thousands of years, making metal was more of an art. It wasn't until 1956, with the discovery of constitutional undercooling, that it truly became a modern engineering science. That's when we got the power to really write the rules.
So does all this work pay off? Oh yeah, big time. In the superalloys they use for jet engine turbine blades, carefully controlling the grain structure can make the blade more than 10 times more resistant to deforming under extreme heat and stress. That's a huge reason why modern jet engines are so incredibly powerful and reliable.
So, when you boil it all down, here's the big idea. By carefully choosing which elements to add, by creating atomic seeds and controlling that solute traffic jam, we can dictate how a material performs on the macro level. It completely changes things. We don't just find materials anymore, we design them. Which leaves us with a really exciting question. With this kind of power, what are we going to build next?